Welcome to Revise and Resubmit, Weekend Classics. I'm Pavlov.
And I'm Nikita.
Today, we're doing something a bit different. We're essentially using, an LLM-generated summary to explore a really fascinating piece of mathematical history.
That's right. We're diving into a truly seminal work called A Synopsis of Elementary Results in Pure and Applied Mathematics by George Shoobridge Carr.
Now, this book, it's got quite a story. Originally published in 2 volumes, the first in 1880.
And the second followed in 1886.
Exactly. And it's maybe most famous because a copy of it landed in the hands of a young Srinivasa Ramanujan. He was only 16 at the time.
Imagine that. Getting this incredibly dense collection, over 4,500 theorems and formulas, often without full proofs, and it just sparks this incredible mathematical journey.
It really makes you think, doesn't it, about how real learning happens. That deep wisdom, empathy, human understanding. You can't just optimize for that stuff. It's lived. It comes from really grappling with material like Ramanujan must have done with Carr's synopsis.
Absolutely, and that's why we wanted to talk about it. Whether you subscribe to our deep dives or not, we genuinely hope you might consider finding this book. It's been republished by the prestigious Cambridge University Press. Beautifully done.
We'll definitely put a link in the show notes for you. It's a thoughtfully, rigorously crafted piece of work, and spending time with it is, well, it's rewarding.
It's a fantastic reminder of the value of these foundational texts. So our mission today is to give you a kind of guided tour through it, volume by volume.
Think of it like walking through a historical landscape of mathematics, seeing what was considered core knowledge back then, how it all fit together. We'll try to approach it as if you're encountering some of these higher mathematical ideas for the first time through Carr's unique perspective.
Okay, so the book itself. A Synopsis of Elementary Results in Pure and Applied Mathematics. That word synopsis is really key.
It means summary, right? An overview. Carr wasn't writing a series of textbooks with every single proof worked out in minute detail.
Exactly. His goal was to compile a huge number of propositions, formulas, methods, but often with just abridged demonstrations, or sometimes none at all.
And why do that? What was the point?
Well, he says in the preface, his main aim was to help readers see the interdependence of mathematical ideas, to trace the connections between different branches.
So by putting everything together, side by side almost, you start seeing the links without having to dig through like 10 different giant books.
Precisely. He believed that unity, that interconnectedness, would become clearer as you worked through his synopsis. It was about the big picture.
And it is a big picture. The title covers Pure and Applied Mathematics. And just looking at the contents lists, wow, it's vast. Thousands of results.
Monumental, really. Volume 1 in 1880, Volume 2 in 1886. And it's great that the Cambridge Library Collection has brought them back, made them accessible again.
Definitely. So let's jump into Volume 1 from 1880. Where does he start?
This might surprise you, actually. Part on is entirely dedicated to mathematical tables.
Tables? Like log tables. That feels almost quaint now, with calculators everywhere.
It does, doesn't it? But back then, these were absolutely fundamental tools. You needed them for any practical calculation. So Carr starts there, providing the essential constants, conversion factors, the groundwork.
What kind of tables are we talking about?
A real mix, which tells you a lot about 19th century maths and science. There's the CGS system of units, centimeter, gram, second, with all the notation and definitions.
Okay, so physics and engineering basics.
Right. Then physical constants and formulae. Tables for converting between English measures and CGS units. Very practical stuff.
Anything more specific?
Oh, yeah. Data related to heat and pressure, like the pressure of aqueous vapor at different temperatures, that's crucial for thermodynamics.
And optics, too.
Yep. Wavelengths and wave frequency for the principal lines of the spectrum. Think spectroscopy, understanding light, maybe even early atomic physics ideas starting to bubble up.
Interesting. What else?
Properties of principal metals, dimensions, masses, densities, and then it lists details about their orbits.
Orbits of metals. That sounds weird. Like electrons.
No, not electrons yet. That threw me for a second, too. Looking at the context, it's almost certainly referring to planetary orbits. So it's data relevant to applied mechanics or astronomy, included alongside material properties. Shows how mixed these fields were.
Okay, that makes way more sense. So mechanics, astronomy data, alongside standard mathematical tables.
Exactly. Powers and logarithms of E and some base A. Common logs, base 10. Hyperbolic logs, base E, natural logs. Even a list of prime numbers, though only up to 109 in the contents list we saw. basic building blocks.
But you mentioned one table got special attention.
Yes, the factor table. It covers numbers from 1 up to 99,000 and gives the least prime divisor for each number.
99,000, that's a lot of factoring.
It is, and Carr calls this, in his preface, the only sort of purely mathematical table which is absolutely indispensable.
Indispensable, why?
His reasoning is interesting. He says you can calculate logarithms using formulas, even if it's tedious. But finding prime factors, back then that mostly relied on trial division, just trying primes one by one. There wasn't a neat formula.
So having a table that gave you the smallest factor was a massive shortcut, a starting point.
Exactly. A fundamental aid for number theory, or any problem that needed factorization. He even notes this part was reprinted from someone else's work, Burckhardt's tables, and acknowledges even bigger tables existed. It shows he was collating the best available tools.
And it wasn't just basic stuff in the tables section, right? You mentioned something more advanced.
Right at the end, values of the gamma function. Now, if you haven't met it, the gamma function, usually written z, is like an extension of the factorial function n. Remember, n is 1, 2, 3 lot for positive integers, well, nn, and 1, but the gamma function works for complex numbers too, not just integers.
Okay, so including that signals, we're already heading beyond really basic maths, even in the tables.
Definitely. It shows the book's scope, even from the start. Elementary clearly meant something pretty broad back then.
Okay, so after the tables, where does Volume 1 go?
Section 2 jumps into algebra. And Carr actually adds a little note in the preface here, saying this algebra section was printed earlier and wasn't revised quite as thoroughly as later parts. He mentions the errata mostly applies to this section. A little glimpse into the publishing process.
So algebra, what's covered? The basics first, I assume.
Starts with foundations, factors, basic multiplication, and division of polynomials. But Carr quickly introduces specific methods, like the method of detached coefficients.
Detached coefficients, how does that work?
It's actually quite clever for speeding up calculations. Say you're multiplying x sextant plus 2x plus 1 by 1. Instead of writing out all the x's, you just use the coefficients.
So 1, 2, 1 for the first one, and 1 add 1 for the second.
Exactly. You arrange them and multiply using just the numbers, keeping track of the place values, which correspond to the powers of x. Then, at the end, you put the x's back in based on the final coefficient positions.
So it cuts down on writing and maybe mistakes.
That's the idea. Makes polynomial arithmetic much more compact. Article 28 gives examples of division using this. Carr also mentions synthetic division, which is a streamlined version of this for dividing by linear factors like xa.
Okay, neat trick. What else in basic algebra?
Covers indices, exponents, highest common factor, HCF, and lowest common multiple, LCM, for algebraic expressions.
Standard stuff. How does he explain finding the HCF?
Article 32 says you factorize everything into simplest factors, then take the product of the common factors, each raised to the lowest power it appears with in any of the original expressions. Article 31 walks through an example. LCM is linked to HCF in the usual way.
Got it. And evolution sounds dramatic.
Yeah, it's just the old term for extracting roots, square roots, cube roots, etc. Article 35 shows how to extract a square root, again using the detached coefficient method. It shows how versatile that technique was seen to be.
Then it moves into sequences and series.
Yep. Defines ratio and proportion. Variation, the idea that if a varies is b, then a equals m for some constant m foundational concepts.
And progressions, AP and GP.
Arithmetical progression, AP, where you add a constant difference d each time, a plus d plus 2p. Articles 79, 82 give the formulas for the nth term and the sum of n terms.
And geometrical progression, Gina.
When you multiply by a constant ratio r each time, A, R, R, R. Articles 83, 86 give the formulas for the nth term and sum. Importantly, it includes the formula for the sum of an infinite GP, provided the absolute value of R is less than 1. That limit concept was considered elementary.
Does he cover anything more complex in series right away?
Yes, the arithmetico-geometrical series, Article 279. This is a mix where each term is an AP term multiplied by a GP term, like a plus DR, a plus 2DR.
How do you sum that?
He gives a neat rule. Multiply the whole series by the ratio R, then subtract this new series from the original one. Most terms cancel out, leaving something manageable. Articles 280 and 283 give specific formulas, including the fundamental 1 plus x plus x plus I is a1 on x.
Okay, series covered. What about counting things? Combinatorics.
That's next. Permutations arrangements where order matters. P and R. The number of ways to arrange R items from a set of n. Article 95 gives the formula n and R.
And combinations. Or order doesn't matter.
CNR. Selections of R items from N. Article 96 gives NR. NR. He notes the symmetry CNR, CNNR.
Just for shortcut.
And Article 97 points out when CNR is largest, when R is around N2. Practical tips.
Anything else in combinatorics?
Homogeneous products, HNR. This is combinations with repetition allowed, like picking R items from N categories where you can pick the same category multiple times. Article 98 gives the formula, which is equivalent to Cn plus R1R. It links this to the binomial theorem, too. Shows connections.
Okay, moving on from counting. Continued fractions. Sounds interesting.
They are. Article 167 defines the form. A0 plus 1, A1 plus 1, A2 plus. It's a way to represent numbers, especially irrational numbers, using a sequence of integers A0, A1, A2.
How do they work?
The key idea is the convergence. Articles 162, 163. These are the rational numbers you get by stopping the fraction at different points.
Like a 0, then A plus 1A1, then A plus 1, A1 plus 1, A2, and so on.
Exactly. And these convergences have cool properties. Article 164 says they alternate being bigger and smaller than the true value, getting closer each time. And crucially, each convergent is automatically a fraction in its lowest terms.
Really? Already simplified. It's handy.
Very. And Article 165 gives a measure of how close each convergent is to the actual value. It's a powerful way to approximate irrationals.
The book covers a lot of ground. What about solving equations?
A huge section on equations. Starts with indeterminate equations. Article 188, usually linear equations with integer coefficients where you want integer solutions, like x plus by equals c. Diophantine equations, essentially.
I don't know what.
A specific technique. Reducing quadratic surds to continued fractions. Articles 195, 199. This is about representing things like scored n as a continued fraction, which turns out to be periodic. Example 124 shows this. It's a deep dive into number theory and approximation.
What about systems of equations? Simultaneous equations.
Number 2 includes the method by indeterminate multipliers, Articles 211, 213, for linear systems, which sounds a bit like Lagrange multipliers maybe, and also methods for tackling systems involving quadratic equations, Articles 220, 222. Lots of algebraic manipulation techniques.
Does it introduce complex numbers here?
Yes. Under imaginary expressions, Article 223, it defines the symbols square 1, which we now call I, and states the crucial rule. It obeys the ordinary laws of algebra. This was a big conceptual step, bringing complex numbers into the elementary framework.
Okay, then methods of analysis. What does that cover?
Key techniques used throughout calculus and beyond. First, the method of indeterminate coefficients, Article 232.
How does that work?
You use it when you assume an identity holds, say, between two polynomials, but you don't know some coefficients. You write out the assumed identity, expand everything, and then equate the coefficients of the same powers of the variable on both sides. This gives you a system of linear equations to solve for the unknown coefficients. Very useful.
Like finding constants in partial fractions.
Exactly. And partial fractions is the next big topic. Absolutely vital for integration. Carr details how to break down a complicated rational function, polynomial over polynomial, into simpler fractions.
Based on the denominator's factors, right?
Precisely. He covers the cases. Distinct linear factors, Article 236, repeated linear factors, example in 236, irreducible quadratic factors, Article 237 gives an example, and repeated quadratic factors, Article 238, a really thorough breakdown of the technique.
What about infinite series?
Big section on series. Articles 239, 240 discuss convergence, and divergence. Does the infinite sum settle on a finite value? It lists various tests, ratio tests, logarithm tests.
And power series specifically, like A0 plus A1x plus A2 by 2 plus rank.
Yes, Articles 241, 242 cover convergence conditions for those, which is fundamental for representing functions like x or sin x. Some specific important series expansions are listed in Articles 284, 285.
Does Volume 1 touch on probability or number theory?
It does. A section on probability covers basics, like the probability of at least one event happening, Article 326, or exactly R-specific events, Article 327, or any R events out of N, Article 328.
Number theory.
Properties of numbers includes things like the sum of divisors of a number, Article 377, Fermat's theorem, likely Fermat's little theorem, Articles 369, 378, relating powers modulo a prime. And Article 379 gives a method to find all divisors of a number, using 504 as an example. Practical number theory.
Wow, okay, the theory of equations section sounds important. What's in there?
It's very detailed. Starts with fundamentals. A polynomial of degree n has n roots. Article 407, fundamental theorem of algebra. Imaginary roots of real polynomials come in conjugate pairs. Article 408, rules connecting signs of coefficients to the number of real roots. Articles 409, 410, like Descartes' rule of signs.
Can you manipulate the equations?
Yes, transforming equations covers techniques like substituting to remove the second term, Article 429, or transforming fxx into an equation for y, where y is some function of x, Article 430, or scaling roots to make coefficients integers, Article 431. Tools for simplifying problems.
What if an equation has repeated roots?
Finding equal roots uses the greatest common measure, GCM, which is like the greatest common divisor for polynomials, between fx and its derivative, fx, Articles 445, 446. Repeated roots are roots of both. Sturm's functions, Article 516, are also mentioned for finding the number of distinct real roots in an interval.
Can you find bounds for the roots?
Yes. Limits of roots gives rules for finding upper and lower bounds, Articles 448, 451. Newton's method for finding a superior limit using derivatives, Article 452. And the basic idea that if FA and FB have opposite signs, there's a root between A and B, Article 453.
What about finding the roots if you can't solve it exactly? Approximation methods.
Mentions Newton's method, Article 521, the iterative Newton-Raphson algorithm. Also a method using sums of powers of roots, Article 548.
Sums of powers of roots? That leads into symmetrical functions, doesn't it?
It does. This is about expressions involving the roots by 1 by 2.xn that don't change if you swap the roots around, like the sum by 1 plus by 2 plus xn, or the product I1 by 2.xn.
Be that as formulas relate those to the coefficients, right?
Yes, and this goes further. Articles 534, 536 give formulas, Newton's sums, for the sums of powers, sk variables by 1k plus xk. Article 537 even uses logarithms of the polynomial. It discusses expressing any symmetric function in terms of these power sums, Articles 538, 539. It even looks at sums of powers of roots of unity, xm1 equals 0, Article 546. Pretty advanced stuff.
And the algebra section finishes with determinants.
Yes. Definitions for 2 by 2, 3 by 3, and general NXN determinants, Articles 554, 545. Methods for calculating them, like cofactor expansion, Article 568. Key properties, like how swapping rows changes the sign, Article 561. How to multiply determinants, Article 573.
And the main application, solving linear equations.
Absolutely. Articles 582, 583 show how to use determinants to find the solution, essentially Cramer's rule. It also covers elimination theory using determinants, like Bezout's method or Sylvester's dialytic method, Articles 586, 587, to find conditions under which two polynomial equations have a common root.
Phew, that's an incredibly comprehensive algebra section for an elementary synopsis.
It really is. It takes you from basic operations right through to abstract structures and powerful computational tools.
Okay, let's shift gears. Volume 1 also covers geometry building on Euclid.
Right. Starts with trigonometrical ratios, sin, complements, tan, etc. Basic identities like sin A plus cos A equals 1. Articles 613, 618.
Standard trig identities, complement, supplement.
Yep. How ratios relate for angles adding to 90 degree or 180 degrees. Articles 619, 622. How to handle angles bigger than 90 degrees. Article 625. Inverse notation, arcsin, etc.
And solving triangles.
A core application. Formulas for different cases, like using the law of cosines if you have two sides and the angle between them, Article 723. Importantly, how to use logarithms for these calculations, Article 724, which was vital pre-calculators.
What else in triangle geometry?
Formulas for area, Article 838, 840. Properties relating to the radii of the inscribed, circumscribed, and ascribed circles, Articles 841, 844. Lots of triangle-specific geometry.
Any particularly interesting formulas mentioned?
There's a section of additional formulas, Articles 8 and 23, 857. Some are standard identities, but Article 858 gives the famous Basel problem result. 11 aboundlet plus 12 analytes plus 13 plus 6x.
Wow, that's usually derived using Fourier series or complex analysis. Why is it in a trigonometry section?
Good question. It's a perfect example of Carr showing unexpected connections. He doesn't derive it there, just states it. It hints at deeper links between trig, series, and analysis.
Fascinating. What about general shapes, quadrilaterals?
Miscellaneous propositions covers things like the parallelogram law relating sides and diagonals, Articles 924 and 925. Geometric constructions based on distance ratios, Articles 926, 928. Properties of triangle centers like the centroid and orthocenter, Articles 956, 927. More on inscribed described circles, Article 959. Constructing triangles from given data, Article 960.
What about points lining up or lines meeting, collinearity, concurrency?
Yes, collinear and concurrent systems introduces classical theorems. Menelaus theorem, Article 968, for when points on the sides of a triangle lie on a line. Sieve's theorem, Article 970, for when lines from vertices to opposite sides meet at a point. Conditions for these are given. Articles 970 and 971. Foundational projective geometry.
I see radical axis listed. What that?
It's about pairs of circles. Articles 986, 989. The radical axis is the set of points where the tangent lengths to the two circles are equal. Turns out to be a straight line. If the circles intersect, it's the line through their intersection points. A more advanced way to relate circles.
An inversion. That sounds like turning things inside out.
Sort of. It's a geometric transformation. Articles 1001, 1009. You pick a circle, the circle of inversion. A point P gets mapped to P on the ray from the center through P, such that the distances multiply to the radius squared.
What does it do?
It has amazing properties. Lines through the center stay lines, but other lines become circles passing through the center. Circles generally become other circles. Orthogonal circles map to orthogonal circles. It can simplify complex geometry problems by transforming figures into easier ones.
Powerful tool. Similitude is next, like similar figures.
Yes. Articles 1037, 1051 deals with figures that are scaled rotated versions of each other. It defines centers of similitude, ratios. It connects to inversion and also to the radical center of three circles. Article 1051. More connections.
And harmonic ratio, or cross ratio.
That's a key concept in projective geometry, Article 152. If you have four lines meeting at a point, a pencil, and cut them with another line, a transversal, at points A, B, C, D, the cross ratio, ACCB, ADDB, is constant, no matter which transversal line you use.
And invariant under projection.
Exactly. Article 10A53 gives a related distance formula. Article 10A56 gives it in terms of angles. It's fundamental for understanding perspective.
Speaking of which, perspective drawing.
Briefly mentioned, Articles 1080, 1086, connecting the abstract geometry to the practical art and technique of representing 3D on a 2D plane. Another applied touch.
And finally, for Volume 1 geometry. Geometrical conics, ellipses, parabolas, hyperbolas.
Yes. Starts with the definition as sections of a cone by a plane. Articles 1151, 1153. Shows how the angle of the cut gives the different curves. Notes parallel sections are similar. Article 1154 mentions limiting cases like circles or lines. Article 1155.
But isn't there another definition involving focus and directrix?
Yes, and Carr presents that as a fundamental property, Article 1151, even proving it using spheres nestled inside the cone, dandelion spheres. A conic is the locus of points where the distance to a fixed point, focus, is a constant ratio E eccentricity times the distance to a fixed line, directrix.
And E determines the shape.
Right. E1 for ellipse, E1 for parabola, E1 for hyperbola. A beautifully unifying definition.
Then he lists properties for each.
Yep. Properties of ellipse and hyperbola, Articles 1204, 1207. Coordinates, conjugate diameters, tangents. Properties of parabola, Articles 1235, 1243, diameters, tangents. The focus reflection property, Article 1241, chord properties.
Does he show how to draw them?
Yes. Practical methods of constructing conics, Articles 1245, 1247. The string method for the ellipse, using the two foci. Ruler methods, bar methods for the hyperbola, string bar for the parabola. Connecting the theory right back to drawing board practice.
That's an incredible amount for just Volume 1. Tables, algebra, from basics to determinants, geometry from Euclid to conics and inversion.
It's staggering, isn't it? And you really see what elementary meant. It was a deep dive into the foundations needed for university-level maths and physics of the time. You can absolutely see how Ramanujan could just devour this, finding thousands of results to play with and build upon.
Okay, let's take a breath and move to Volume 2 from 1886. Where does this one pick up?
Volume 2 delves more into what we'd now call analysis and higher applied mathematics. It starts with the expansion of explicit functions.
Series expansions, like Taylor series.
Exactly. Taylor's theorem, Article 1503, is central, representing a function as an infinite sum based on its derivatives at a point. Carr includes Lagrange's form of the remainder term that's crucial for estimating the error if you truncate the series.
Does he discuss when these series actually work? Convergence.
Yes, Article 1504 mentions conditions for convergence, and Articles 1505, 1506 note when the series might fail or diverge. Maclaurin's theorem, Articles 1507, 1508, is presented as the special case where you expand around x plus 0.
Any pitfalls mentioned?
He explicitly notes Article 1509 when Maclaurin's theorem can't be applied if the function or any derivative blows up at x is 0. He uses arcsin 1 plus x as an example. The function's okay at x is 0, but its derivative isn't. Important subtleties.
What other series expansions?
Bernoulli's series, Article 1510, is mentioned. And the next section, expansions of functions in series, seems to touch on Fourier series ideas.
Fourier series for periodic functions.
Looks like it. Article 2962 gives an expansion of Ex, using signs. And Article 2964 emphasizes a key Fourier concept. The series might represent the function only within a specific interval.
Like representing a square wave or a sawtooth wave.
Precisely. Article 2968 gives an example of representing a piecewise function, like Tx, then KLSX. It also mentions conditions on the function's integrability for the series to be valid. Articles 2964, 2965.
Moving beyond series.
Includes approximate integration, Article 2991, recognizing that you can't always find exact integrals, so numerical methods are needed. Very practical.
And then a huge topic, differential equations.
Yes, a major area of higher maths. Equations linking functions and their derivatives, essential for modeling change.
What kind does Carr cover?
The examples, Articles 3545, 3546, suggest various types. Equations with homogeneous functions, ones reducible by substitution using symbolic operator methods, even first-order linear partial differential equations, PDEs, involving multiple variables, Articles 3548, 3549.
Does it show how to solve them all in detail?
Following the synopsis style, it seems he presents the type of equation and maybe the general form of solution or the standard method rather than full derivations. It's a catalog of forms and techniques. If you see this, try this.
Like a field guide to differential equations?
Kind of, yeah. Pointing you in the right direction.
Volume 2 also has theory of plane curves. Specific examples.
Yes, exploring particular curves with interesting properties. The logarithmic curve, Article 5284. Its defining feature is a constant subtangent. Equation y equals AENX.
And the equiangular spiral.
Also known as the logarithmic spiral, Article 5288. Here, the angle between the radius vector and the tangent is constant. Equation r equals A and theta. Famous for appearing in nature shells, galaxies.
More obscure ones.
The syntractrix, Articles 5282, 5283. It's traced by a point on the tangent line of another curve called the tractrix, maintaining a constant distance from the point of tangency. He gives its equation too. Shows the level of detail in specialized geometry.
So Volume 2 covers analysis, DEs, specific curves. How does it wrap up?
With something really revealing about the book's purpose. A joint index, page 5p.
Joint. Indexing what?
Not just Carr's synopsis itself, but also referencing papers on pure mathematics from contemporary British and foreign journals and society transactions.
Whoa! So it's a bibliography too, a guide to the actual research literature.
Exactly. The key to the index, page 5x, lists symbols for different publications. You could look up, say, determinants in Carr, get the basic results, and then use the index to find references to original papers with full proofs or further developments.
That makes so much sense of the synopsis approach. It wasn't meant to be self-contained, it was a gateway.
Precisely. It addresses that quote attributed to Professor J.D. Everett, page 5p. There is an immense amount of knowledge lying scattered, and almost useless from the difficulty of finding it when wanted. Carr's work was an answer to that problem.
Gathering it all, structuring it, and pointing towards the deeper sources. A reference, a study aid, a map.
A map is a great way to put it. A map of the mathematical landscape of the late 19th century.
So looking back at both volumes, what's the big takeaway?
You see this incredible breadth. From basic arithmetic tools and algebraic techniques, through classical and advanced geometry, into calculus, differential equations, complex functions, specific curves. It's a snapshot of a huge body of knowledge.
And the elementary label is definitely relative. A lot of this is advanced undergraduate material today.
Absolutely. But it shows Carr's vision, presenting this vast range, highlighting the connections he felt were important, and providing thousands of specific results as starting points.
For someone learning then, or even exploring now, it's like getting a catalog of mathematical ideas. You can browse, see what relates to what, pick a result, and try to understand it or find its proof.
It's an invitation to discovery even without every step being laid out. Each numbered article is a nugget of mathematical knowledge.
It really makes you think about how we organize and access knowledge today, with search engines and digital archives. Carr's curated, interconnected structure offers a different kind of navigation.
And maybe a final thought. Does the way knowledge is structured influence what we discover? Carr put things together in ways that might seem unusual now, like that Sussex formula in trigonometry, or planetary data next to metal properties. Does that juxtaposition itself spark new insights, highlighting unexpected links between pure and applied ideas, just as he intended?
That's a fascinating question to ponder. What an incredible journey through this historical text. Thanks for guiding us through Carr's synopsis.
It was a pleasure. It's a real testament to the effort involved in consolidating knowledge and the lasting impact such works can have. Hopefully it inspires some listeners to seek out these kinds of foundational texts.
Absolutely. Thanks for joining us. And don't forget to subscribe to Revise and Resubmit on Spotify and Apple Podcasts. Until next time, keep those minds curious, keep questioning, and keep revising and resubmitting.
রিভাইজ অ্যান্ড রিসাবমিটের উইকেন্ড ক্লাসিক্স পর্বে আপনাদের স্বাগত। আমি পভলভ।
আর আমি নিকিতা।
আজকের আলোচনা একটা বেশ অন্য রকম বই নিয়ে, জর্জ শুব্রিজ কারের লেখা Synopsis of Elementary Results in Pure and Applied Mathematics।
হ্যাঁ, আর এটা সারসংক্ষেপ কিন্তু আমরা একটা লার্জ ল্যাঙ্গুয়েজ মডেল থেকে পেয়েছি।
ঠিক, বইটা আসলে দুটো ভলিউমে। প্রথমটা বেরিয়েছিল 1880 সালে আর দ্বিতীয়টা 1886-তে।
বেশ পুরনো। আর সবচেয়ে মজার ব্যাপার হলো শ্রীনিবাস রামানুজনের সাথে এর সংযোগ।
তাই তো, মাত্র 16 বছর বয়সে এক বন্ধু ওকে এই বইটা দেন, ভাবা যায়।
আর বইটাতে ছিল প্রায় 4,500, তারও বেশি উপপাদ্য আর সূত্র, কিন্তু কোনো প্রমাণ ছিল না।
প্রমাণ ছাড়া? এটাই তো অদ্ভুত লাগে শুনতে।
হ্যাঁ, কিন্তু ওটাই ছিল কৌশল। পাঠককে নিজে থেকে প্রমাণ খুঁজে বার করতে হতো, ভাবতে হতো, সংযোগ তৈরি করতে হতো বিভিন্ন শাখার মধ্যে।
যেটা হয়তো আলাদা আলাদা বই পড়ে সহজে পাওয়া যায় না।
একদম, এটা অনেকটা সক্রিয় পাঠ, শুধু তথ্য নেওয়া নয়।
আর এই গভীর পাঠের বিষয়টা এটা মনে করায় যে জ্ঞান বা মানবিক বোঝাপড়া এগুলো তো অপটিমাইজ করার জিনিস নয়, এগুলো অভিজ্ঞতার মধ্যে দিয়ে আসে।
ঠিক বলেছেন। রামানুজনের জন্য নিশ্চয়ই এই বইটা সেরকমই এক গভীর অভিজ্ঞতা ছিল।
তো আমাদের আজকের লক্ষ্যটা কি? কাদের জন্যই আলোচনা?
আসলে যারা উচ্চতর গণিতের জগতে নতুন বা এই বইটা নিয়ে কৌতূহলী, তাদের একটা ধারণা দেওয়া, বইটার ভেতরে কি আছে সেটার একটা ঝলক।
বেশ, চলুন তাহলে প্রথম খণ্ডটা দিয়ে শুরু করা যাক। এর প্রথম অংশটা তো গাণিতিক সারণী, তাই না? ম্যাথমেটিক্যাল টেবলস।
হ্যাঁ, ঠিক। এখানে মূলত সেই সময়ের দরকারি কিছু ভৌত ডেটা আর কি। ধরুন, সিজিএস পদ্ধতিতে একক, নানা রকম ফিজিক্যাল কনস্ট্যান্ট, পদার্থের ঘনত্ব, স্থিতিস্থাপকতা।
তৎকালীন বিজ্ঞানীদের জন্য কাজের জিনিস।
অবশ্যই। জলীয় বাষ্পের চাক, বর্ণালীর তরঙ্গ দৈর্ঘ্য, রোধকত্ব, এমনকি গ্রহদের মাপ, ভর, কক্ষপথের তথ্যও ছিল।
ফ্যাক্টর টেবিল, গামা ফাংশনের মান, এসবও।
বাহ। আর দ্বিতীয় অংশটা, ওটা তো বীজগণিত নিয়ে। হ্যাঁ, দ্বিতীয় অংশটা মূলত অ্যালজেব্রা, একদম বেসিক থেকে শুরু। ধরুন, দ্বিপদী উপপাদ্য, সংখ্যার গুণ ভাগ করার কিছু বিশেষ পদ্ধতি, যেমন ডিট্যাচড কোএফিসিয়েন্ট।
আচ্ছা, তারপর
ধরুন গসাগু, লসাগু HCF LCM, সমান্তর আর গুণোত্তর প্রগতি, অ্যারিথমেটিক্যাল জিওমেট্রিক্যাল প্রোগ্রেশন যাকে বলে।
হ্যাঁ, মনে পড়ছে। পারমিউটেশনস, কম্বিনেশনস, বিন্যাস, সমাবেশ।
ঠিক, কত রকমে সাজানো যায়, বাছা যায়। তারপর আছে কন্টিনিউড ফ্র্যাকশনস, ধারাবাহিক ভগ্নাংশ, সমীকরণের তত্ত্ব, থিওরি অফ ইকুয়েশনস।
পার্শিয়াল ফ্র্যাকশনস, সিরিজ, সম্ভাব্যতা প্রবাবিলিটি, থিওরি অফ নাম্বারস সংখ্যাতত্ত্ব। বেশ বিস্তারিত আলোচনা তাহলে।
হ্যাঁ, বেশ গোছানো। ইউক্লিডের জ্যামিতির কিছু স্বীকার্য, প্রপোজিশনস অফ ইউক্লিড, আর ত্রিকোণমিতির নানা সূত্র, পদ্ধতি, এসবও ছিল।
আচ্ছা, আর বই শুরুতে নাকি একটা ভুল সংশোধনী তালিকাও ছিল, এরাটা।
হ্যাঁ, ছিল। এটা কিন্তু লেখকের যত্ন আর একনিষ্ঠতার প্রমাণ দেয়। ভাবুন, রামানুজন এই সব সূত্রগুলো পেয়েছিলেন প্রমাণ ছাড়াই। ওকে নিজে থেকে এগুলোর সত্যতা যাচাই করতে হয়েছে।
দারুণ ব্যাপার। আচ্ছা, এবার যদি দ্বিতীয় খণ্ডের দিকে যাই, সেটা নিশ্চয়ই আরও একটু গভীরে গেছে।
অবশ্যই। প্রথম খণ্ডের ভিতের ওপর দাঁড়িয়ে দ্বিতীয় খণ্ডটা মূলত ক্যালকুলাস আর তার প্রয়োগ নিয়ে।
যেমন
ধরুন, ফাংশনের বিস্তার, এক্সপ্যানশন অফ ফাংশনস, টেইলর সিরিজ, ম্যাকলরেনের সিরিজ, বার্নাউলির সিরিজ, কিভাবে একটা ফাংশনকে অসীম ধারায় লেখা যায়।
ও আচ্ছা, ফুরিয়ার সিরিজও কি ছিল?
হ্যাঁ, ফুরিয়ার সিরিজের কথাও আছে। বিভিন্ন ফাংশনের সিরিজ এক্সপ্যানশনের উদাহরণ দেওয়া হয়েছে। এটা তো সিগন্যাল প্রসেসিং বা ওয়েভ অ্যানালিসিসে খুব জরুরি একটা টুল।
আর ডিফারেনশিয়াল ইকুয়েশন অন্তরক সমীকরণ?
হ্যাঁ, ওটাও খুব গুরুত্বপূর্ণ অংশ। লিনিয়ার, পার্শিয়াল রৈখিক আর আংশিক, দুরকম ডিফারেনশিয়াল ইকুয়েশনের সমাধানের পদ্ধতি আলোচনা করা হয়েছে।
বিজ্ঞানের নানা মডেল তৈরিতে তো এটা লাগেই।
একদম। এছাড়া আছে প্লেন কার্ভসের তত্ত্ব, থিওরি অফ প্লেন কার্ভস। ধরুন লগারিদমিক কার্ভ বা ইকুইঅ্যাঙ্গুলার স্পাইরাল। এই স্পাইরালটা তো প্রকৃতিতে খুব দেখা যায়, শামুকের খোলে বা গাছের পাতায়।
তাই নাকি? আর কি ছিল?
কোয়াড্রেচার মানে ক্ষেত্রফল নির্ণয়, ভর কেন্দ্র বা সেন্ট্রয়েডস খোঁজা, এই ধরনের জ্যামিতিক বিষয়গুলো। আর শেষে একটা জয়েন্ট ইন্ডেক্স ছিল, যেটা অন্যান্য গবেষণাপত্রের সাথে লিঙ্ক করতে সাহায্য করত।
তাহলে সব মিলিয়ে দেখলে কারের বইটা শুধু সূত্রের একটা লিস্ট নয়, বরং এটা গণিত চর্চার একটা অন্যরকম পথ দেখায়।
ঠিক, প্রমাণ না দিয়ে পাঠককে নিজে থেকে আবিষ্কার করতে উৎসাহিত করা।
আর রামানুজনের মতো জিনিয়াসের উপর এর যে প্রভাব, সেটাই বোধহয় বইটার গুরুত্ব সবচেয়ে ভালোভাবে বুঝিয়ে দেয়।
নিঃসন্দেহে এই বইটা কিন্তু ওই সারসারি চোখ বোলানোর মতো নয়, ধৈর্য ধরে চিন্তা ভাবনা করে পড়ার মতো।
হ্যাঁ, সেটাই। আর কেমব্রিজ ইউনিভার্সিটি প্রেস থেকে যে পুনঃপ্রকাশিত সংস্করণটি পাওয়া যায়, সেটা সংগ্রহ করার জন্য আমরা অবশ্যই শ্রোতাদের উৎসাহিত করব।
হ্যাঁ, পড়ার অভিজ্ঞতাটাই অন্যরকম হবে। বইটার লিঙ্ক আমরা শো নোটসে দিয়ে দিচ্ছি।
আর শেষে আবার সেই কথাটা মনে পড়ছে, এই ধরনের গভীর পাঠ এটা আবার মনে করিয়ে দেয় যে আসল জ্ঞান মানে প্রজ্ঞা বা মানবিক বোঝাপড়া, এগুলো কোনো অপটিমাইজেশনের ব্যাপার নয়।
না, এগুলো অভিজ্ঞতার মধ্যে দিয়ে অর্জন করতে হয়, লিভড এক্সপিরিয়েন্স যাকে বলে।
একদম। আজকের মতো তাহলে এখানে শেষ করি। ধন্যবাদ।
ধন্যবাদ।
नमस्कार और रिवाइज एंड रीसबमिट की वीकेंड क्लासिक्स एपिसोड में आपका स्वागत है। मैं हूं पाब्लो
और मैं हूं निकिता।
आज हम एक बहुत ही खास किताब पर बात करने वाले हैं, जीएस कार की सिनॉप्सिस ऑफ एलिमेंट्री रिजल्ट्स इन प्योर एंड अप्लाइड मैथमेटिक्स। और मजे की बात यह है कि इस चर्चा का आधार, इसका जो सारांश है, वो एक लार्ज लैंग्वेज मॉडल ने तैयार किया है।
हाँ, ये बहुत दिलचस्प किताब है और ये 2 वॉल्यूम में आई थी, मतलब 2 खंडों में। पहला आया 1880 में और दूसरा वो आया 1886 में।
अच्छा, 2 खंडों में। और यही वो किताब है जिसने, कहते हैं, महान गणितज्ञ श्रीनिवास रामानुजन की जिंदगी पर बहुत गहरा असर डाला।
बिल्कुल, उन्हें ये किताब तब मिली जब वो सिर्फ 16 साल के थे, किसी दोस्त से मिली थी। और इसमें आप सोचिए 4500 से ज्यादा प्रमेय और सूत्र हैं।
4500, बाप रे। लेकिन इसमें एक पेंच है ना?
हाँ, पेंच ये है कि इसमें इन थ्योरम्स या फॉर्मूलों के प्रूफ्स, मतलब उनके प्रमाण या वो कैसे निकले, ये सब नहीं दिया गया है, बस रिजल्ट्स हैं,
सिर्फ नतीजे। ये तो बड़ी अनोखी बात है। तो आज हम कोशिश करेंगे कि इन दोनों खंडों में क्या है, इसका एक मोटा मोटा आइडिया दे सकें, खासकर उनके लिए जो हायर मैथ्स में, मतलब उच्च गणित में नए हैं।
हाँ, और एक बात और, इस किताब को अब कैम्ब्रिज यूनिवर्सिटी प्रेस ने फिर से छापा है, जो अपने आप में बड़ी बात है। तो हम श्रोताओं से कहेंगे कि अगर मौका मिले तो इसे देखें जरूर। लिंक हमने शो नोट्स में डाल दिया है।
बिल्कुल। तो चलिए पहले खंड से शुरू करते हैं, जो 1880 में आया था। इसमें क्या था? क्या ये बिल्कुल बेसिक से शुरू करता है?
हाँ, पहला खंड एकदम बुनियाद रखता है। शुरुआत होती है गणितीय तालिकाओं से, मैथमेटिकल टेबल्स, जैसे इकाइयाँ, स्थिरांक, लघुगणक यानी लॉग्स, अभाज्य संख्याएं, वो सब जो आपको कैलकुलेशन में काम आती हैं।
अच्छा, मतलब एक तरह का रेडी रेकनर जैसा?
हाँ, कुछ वैसा समझ लीजिए। और उसके बाद ये सीधे अलजेब्रा यानी बीज गणित में उतरता है।
अलजेब्रा, उसमें क्या क्या कवर किया है?
उसमें काफी कुछ है, जैसे सीरीज है, अरिथमेटिक, ज्योमेट्रिक प्रोग्रेशन, फिर परम्यूटेशन कॉम्बिनेशन है यानी क्रमचय और संचय, बाइनोमियल थ्योरम है।
ओके।
और थ्योरी ऑफ इक्वेशंस, मतलब समीकरणों का सिद्धांत, जिसमें डिटर्मिनेंट्स वगैरह भी आ जाते हैं, अनुपात, समानुपात, ये सब।
तो मतलब अलजेब्रा पर काफी फोकस है। और ज्योमेट्री, ट्रिग्नोमेट्री?
हाँ, वो भी है। चामिति और त्रिकोणमिति की भी बेसिक्स कवर किए हैं, यूक्लिड के जो प्रोपोजिशंस हैं उनका हवाला देते हुए। लेकिन यहाँ भी जोर नतीजों और फॉर्मूलों पर ही है, डिटेल्ड डेरिवेशन या प्रूफ्स नहीं।
समझ गया। तो ये एक तरह की गणितीय टूल किट हुई जिसमें सारे औजार रख दिए हैं, पर ये नहीं बताया कि वो बने कैसे।
बिल्कुल सही,
बस एक रेफरेंस गाइड जैसा। दिलचस्प है। तो ये था पहला खंड। अब आते हैं दूसरे खंड पर, 1886 वाला। ये कहाँ ले जाता है हमें?
यहाँ से, जैसा आपने कहा, मामला और दिलचस्प और गहरा होता है। दूसरा खंड पहले पर ही आगे बढ़ता है और हायर मैथमेटिक्स की तरफ जाता है।
उच्च गणित, मतलब कैलकुलस वगैरह?
हाँ, बिल्कुल। कैलकुलस इसका एक बहुत बड़ा हिस्सा है। डिफरेंशियल कैलकुलस, इंटीग्रल कैलकुलस।
अच्छा, अवकलन और समाकलन।
हाँ, वही। और कैलकुलस ऑफ वेरिएशंस भी है, कैलकुलस ऑफ फाइनाइट डिफरेंसेस भी है। इसमें टेलर सीरीज, मैक्लॉरिन सीरीज, फूरियर सीरीज जैसे ज़रूरी टॉपिक्स भी शामिल हैं।
वाह, ये तो काफ़ी एडवांस्ड हो गया। कैलकुलस के अलावा और क्या था दूसरे खंड में?
कैलकुलस के अलावा इसमें कोऑर्डिनेट ज्योमेट्री है, प्लेन और सॉलिड दोनों, मतलब समतल और ठोस ज्यामिति, और डिफरेंशियल इक्वेशंस यानी अवकल समीकरण।
ओके, तो ये गणित के नक्शे को और बड़ा कर देता है ना?
हाँ बिल्कुल, इसमें ज्यादा एडवांस टूल्स और कॉन्सेप्ट्स दिए गए हैं।
तो अब सबसे बड़ा सवाल, ये किताब जिसमें सिर्फ नतीजे थे, प्रूफ थे ही नहीं, वो रामानुजन जैसे जीनियस के लिए इतनी महत्वपूर्ण कैसे बन गई? ये थोड़ा अजीब नहीं है?
हाँ, पहली नजर में अजीब लग सकता है, पर शायद यही इसकी खासियत थी। देखिए, ये कोई आम टेक्स्ट बुक तो थी नहीं जो आपको शुरू से सब कुछ सिखाए। ये उस वक्त तक मालूम गणितीय नतीजों का एक बहुत ही घना कंडेंस्ड संग्रह था।
तो रामानुजन के लिए ये एक तरह का खजाना था?
हाँ बिल्कुल, रामानुजन जैसे तेज दिमाग के लिए ये गणितीय विचारों का एक खजाना था। प्रूफ न होने का शायद ये मतलब हुआ कि उन्हें कई कनेक्शंस खुद जोड़ने पड़े, कई चीजों को खुद साबित करके देखना पड़ा होगा।
मतलब इसने उन्हें सोचने पर मजबूर किया, नए रास्ते तलाशने पर।
हाँ, ऐसा लगता है। ये किताब एक तरह से उस समय की ज्ञात गणितीय दुनिया का नक्शा थी। इसने उन्हें न सिर्फ ये दिखाया कि क्या क्या पता है, बल्कि शायद उन गैप्स को भी उभारा जहां और खोज की जा सकती थी। ये एक लॉन्च पैड जैसा बन गया उनके लिए।
वाकई, तो ये किताब सिर्फ एक कलेक्शन नहीं थी, बल्कि एक तरह की चिंगारी थी जिसने रामानुजन की प्रतिभा को और भड़काया।
सही कहा। ये दिखाता है कि ज्ञान को पेश करने के अलग अलग तरीके कैसे अलग अलग तरह की सोच को प्रेरित कर सकते हैं।
तो कार की सिनॉप्सिस मतलब गणितीय ज्ञान का एक असाधारण संकलन तो है ही, लेकिन जैसा रामानुजन ने दिखाया, ये अप्रत्याशित खोजों के लिए एक शुरुआती बिंदु भी बन सकती है। आज भी एक अहम रेफरेंस बुक है ये।
और यहीं पर हम श्रोताओं के लिए एक सवाल छोड़ सकते हैं। आज के जमाने में जब जानकारी इतनी आसानी से उपलब्ध है, क्या कार की किताब जैसा कोई संग्रह जिसमें सिर्फ नतीजे हों, डिटेल्ड एक्सप्लेनेशन ना हो, क्या वो आज भी गणितीय खोज या जिज्ञासा को उसी तरह से जगा सकता है?
सोचने वाली बात है। इस पर जरूर सोचिएगा। और अगर आप कार की किताब देखना चाहें तो लिंक शो नोट्स में है। आज के लिए बस इतना ही। धन्यवाद।
धन्यवाद।